Okay, let's start. Good afternoon. Any questions before I move to the material? Okay, so a bit of an announcement. So I couldn't make it to the campus in time for my office hours today. So I'm going to hold the office hours right after the lecture. So you are welcome to come by. They will be in my office as opposed to the lab that we had last time. So again, a reminder on Friday evening, 6 to 8, I'll be holding this midterm review session. And I haven't received any questions. So I think, again, I'll urge you that for it to be effective, it's important that sort of you come up with some questions, send them to me so that sort of we can go through them. Otherwise, it becomes rather boring. Also, the other thing is the way we'll do the session is I will have you come to the board and solve. We had a bit of a practice run for that last time. I'll probably be doing more and more of that as the course evolves because I want you to be engaged a bit more. Um, Okay, so today's plan is that we are actually going to move to post-midterm material. Other than the first 5 minutes, I'm going to just do a bit of a recap. And in particular, not just post-midterm, we'll also move to post-combinational. That is, thus far, we were primarily looking at stuff which was memoryless. And early on, we had talked about that how there are circuits which remember stuff. So we are going to start moving to those. But before I do that, just to recap, we had looked into various kind of number representations and how to do arithmetic over them. And towards the very end, in a sort of a very superficial fashion, I also mentioned that there are other ways, other forms of numbers which go beyond integers or positive numbers and signed integers to ones where we start worrying about real numbers. And in particular, I had talked about that how we have fixed point numbers, where essentially they're kind of like integers, except that we imagine that there is a dot that divides the integer in the fractional part. And otherwise, the only thing that happens is that the weights for the fractional part go as 1/2, 1/4, 1/8, 1/16, and so on and so forth. So it's as if this whole this dot is as if I had an integer which I had divided by a certain power of 2. In this particular case, by 2 to the power 5, so it's by a factor of 32. So if that's all we were dealing with, things are rather easy to do because I can continue using my integers, the same adders and all, except that keep track of this decimal place. And again, remember the rule that whenever we are adding things, whenever we are adding bits, bits of the same weight have to add. So if, for example, I were to give you yet another number, just let me kind of set things up a little bit here. Let's say I were to give you two binary fixed point numbers. Okay, so one was the one which we have 11011 dot 00101. Okay, and another number, let's say I gave you, was 11.01. Well, for us to add them, much like the way we do it in decimal thing, we'll have to make sure that uh, these periods are aligned, the dots are aligned. Okay, so I'll have to add it like this: 11011 dot 00101, and then 11.01, and then we can extend it by zeros here. And on this direction, we can again extend it. If assuming these are all positive, we'll extend it by zeros. If it was 2's complement, we'll have to do something differently. But in this case, they were all positive, and only then we can add. Okay, and so as long as we keep these dots aligned, then it's no different than integer arithmetic with kind of a mental weight being carried on. If you are uncomfortable with this, what you can always do is you can think of this first number as some number divided by 32 and keep track of that divide by 32 elsewhere. And this particular number is 1101 divided by 4. That's why we have the dot out here. And then think of the following: if I were to ask you to add two fractions, something over 32 plus something over 4. So in our case, 11011000101 over 32 and 1101 over 4. Then the way we are taught to add fractions is to make the denominator the same. So the second number would become 8 times 1101 divided by 32. And 8 times 1101 is nothing but 1101000, okay, which is what we have out here, 1101000. And now we have the same denominator for the two, so I can go ahead and add the numerator. And once I have the numerator, then I can divide the whole thing by 32, which is again dividing kind of a right shift kind of an operation. So just as long as you keep in mind that the weights have to be the same, or if you're thinking in terms of fractions, the divisor is the same, then it just follows the standard rules of arithmetic. Okay. And the other thing again, remind, whenever you add in things, the bits that you are adding, their weights have to be the same. Otherwise, it's an invalid addition. So that's binary fixed point, and this is the cheap way of doing real number arithmetic. So you can just use the standard integer instructions and all, and then just by programming language support, you can kind of use your integer hardware to do real number arithmetic. The problem which comes in this kind of approach is that let's say I give you 32 bits. Well, I really cannot. If I increase the fractional size, then I have to sacrifice on the integer side, and the powers of the magnitude of the number I can represent is not very good. And also, anytime I multiply things start getting crazy. So let's say I multiply some number a over a number like, so let's take two numbers. So let's say I take this number 1101, which as I just said, 1101 represents 13 over 4. And let's say I give you another number, let's say 01.11, that is 7 over 4. Okay, and if I were to add, I'm okay because the denominator is same, but the moment I multiply them, then 13 over 4 multiplied by 7 over 4 suddenly gives me 13 times 7, which is 91, 91 divided by 16. So now I have a different factor attached to it, and that would mean that the product would have 4 digits to the right of this binary point. And so with binary fixed point arithmetic, multiplication, division start getting a bit painful because the weight I have attached to these numbers keeps changing as my program runs. Okay, so whenever I multiply things, and if I keep multiplying, like if I'm doing repeated multiplication, the weight keeps on changing, and we have to repeatedly kind of keep track of it. So that becomes painful. So this is why floating point numbers were invented. So the idea in floating point is that we keep our mantissa part to be always have a decimal point at a fixed location, typically at the very front, and then keep the powers separate. Okay, I think this one is probably a typo. I think this is 2 to the power 101. Okay, but the idea is that we separate out the power and we just keep the mantissa component to be in a fixed form. And this is what has resulted in the this is what is float and real and double in your programming languages. And there are so-called single precision floating point numbers, which are packed into 32 bits. And then there are also something called double precision floating point numbers, which use 64 bits. And I think newer programming languages and all also have support for 128-bit things. But in any case, what we do is in the same 32-bit, we pack mantissa, an exponent, and the sign. So for example, one possible representation could be I use 1 bit for the sign, I use a certain number of bits, 23 bits for the mantissa, and I use 8 bits for the exponent. And I could have something like this. There is a standard called IEEE 7754, in which case there's some additional magic which sort of goes on out here, where there is a bias term and there is the actual mantissa is 1 plus m. There's a lot of work which has gone on behind this, because even a tiny bit of error in these floating point things can translate into huge discrepancies in results in scientific computation, and you may end up with like instead of the weather model predicting that the hurricane is going to land in city A, it might land in city B. I mean, these errors kind of just build up. So much of the research and kind of standards in this field are driven by the needs of scientific computation, kind of stuff that US government does, or like nuclear bomb simulations and all these kind of things, gigantic scientific computations. So a lot of effort has gone into kind of making sure that these things work the way they would expect. There will not be a buildup of errors and things like that. Much more advanced topic than what we can do in a course like this. But as I mentioned, there is actually a pretty nice class in course in computer science, which Professor Miloš Ercegovic teaches. It's entirely on computer arithmetic, and kind of pretty fascinating class. So your choice of numbers and all, what representation to use, will usually be driven by kind of your application domain. So let's say I was designing some sort of a system to deal with temperatures and all, and I had a need to represent 0 through 100 degrees Celsius in 0.1 Celsius resolution. That is, I want to be able to express things like 77.7 and but no more. So I don't need anything further beyond the decimal point. So in this particular case, if we were doing things in decimal, we would basically say that, look, I need 3 digits to the left of the decimal point, and I need 1 digit to the right of the decimal point. So I need a total of 4 decimal digits. Okay. If we were to think in terms of binary, so since we want to do 0.1 degree C, so that means I need to be able to represent 1 over 10. Now 1 over 2, 1 over 4, 1 over 8, these are still 2 cores. I need to go to 1 over 16. So that means I will need 4 bits to the right of the fractional point. And to the left, I need to represent up to 100, which means I need 7 bits. So in case of a binary representation, so in case of a decimal representation, it would go like D, D, D for the decimal digits, dot D. In case of a binary, this would look like bit, 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 and bit. 7 bits because 64 is too small, 128 is what we are needed. And then to represent 0.1, we need 1 over 10, so we need to go down to 1 over 16. So I will need 7 plus 4, 11 bits out here. Okay, to represent this. So again, and then once we have that, so you can think of it as I have an 11-bit number, but we'll always mentally imagine that this whole thing has been divided by 16. Okay, and then keep track of this. So we can add temperatures, we can subtract temperatures. If we multiply temperatures, then the temperature square will have a weight of what? Anyone? So if temperature has a weight of 1 over 16, then temperature square will have a weight of 1 over 16 times 1 over 16. So I will then end up with 8 bits to the right of the fraction point, and then I'll have to kind of let go of some of them to keep track of things. So that's what's going to happen. Now, what kind of error am I going to see? So if you think about it, 0.1 is something. So let's say I want to represent the temperature 0.1 degree, okay, or whatever, 1.1 degree, okay. So the integer part I can certainly represent accurately in my 7 bits to the left of the fraction point. What about 0.1? Can I represent 0.1 precisely? Now let's try. So 0.1 is 1 over 10. So the smallest thing I can represent is 1 over 16. Okay, now if I were to just leave it at that, if I were to represent 0.1 as 0.0001, then I'm representing 1 over 16, whereas I really needed 1 over 10, so there is an error. Okay, what else can I do? I can add 1 over 8 to it, right? That's the next smallest thing I can add. Well, in that case, it is equal to 3 over 16, which is unfortunately too large than 1 over 10, so I cannot use that either. So I'll have to, so inevitably when I'm going fractional, I am going to have some error being introduced. Okay, so because I cannot represent 0.1 exactly in binary. And this is again something to kind of keep track of. So again, in scientific computing and all, these errors are going to matter. So while you may think you're feeding correct values, internally the computer has to quantize. I mean, this is a form of a so-called quantization error that is happening. So computer arithmetic is a little bit tricky. So for example, A minus B, if A and B are well, let me word it this way. Let's say we were to do something like a minus b plus b, okay? Then by arithmetic rules, a minus b plus b is always going to be a. But in computer arithmetic, what may happen is when I first do a minus b, there may be a bit of an error. And then when I do a plus b again, that error may retain, and the answer may not be a. It may be actually something different than a. So the standard rules of arithmetic do not necessarily hold true because of these numerical errors. Okay, and these are things which people who do sensitive numerical computation, the physicists and all, they kind of worry a lot about, because you do not want your results to be corrupted by kind of these subtle things which are creeping in. Again, these topics kind of they're not terribly deep. You can kind of rationalize about them based upon arithmetic that we do by high school, but these things do end up sort of becoming important. Okay, so so fixed point, floating point, accuracy, resolution, these are kind of things. Okay, so I'm going to stop on this module, and we are going to start on an entirely new topic now, and which is sequential logic. So with sequential logic, we are making kind of a big transition, and this is a difficult topic at some level. So I think you'll have to kind of just try to pay some attention and ask questions, because we're going to be introducing some additional concepts in a very rapid fashion. So combinational logic, if you recall, way early on I had said that combinational logic, the idea is I'm designing hardware, or I'm designing circuits or systems which have no memory. So if I change the input, then the output changes immediately, ignoring any sort of physical tiny amounts of delays that may happen in the gate. But I change the input, the output follows. It's not a function. In particular, after the circuit has settled, the output is only a function of what the current input is. Okay, it does not depend upon what the previous input was. And that's of course extremely limiting, because I cannot do a lot of interesting stuff. Like, for example, I would say that the output should be the sum of the current input and the input which was there before that. Okay, I cannot do things like that. So I need to somehow introduce a notion of memory, something which remembers what happened in the past. So circuits that remember memory are called sequential circuits. Now, and very very trivially, history means everything that has happened thus far. The problem with history is that history is infinite. Okay, we can kind of keep going back in the time, and over time the circuit may have seen lots of different inputs coming in, and if I have to maintain all the history, then that would mean essentially I have to keep track of every input that was ever seen. Okay, so for example, let's say I am designing a system which for a parking lot, and what it does is that it keeps track of how many cars are entering and leaving, and what I want to know is when a new car enters, how many cars are in the parking lot, or car exits, how many cars are in the parking lot. Now, if you think about it, one way of looking at this problem in terms of history would be, I keep track of every car that ever entered and every car that ever left thus far. So I kind of keep a log of each one of them. And every time a new car comes, I go back to my history and I say, okay, this is a new car which is coming in. How many other cars had come in? How many other cars had left previously? And I kind of go through my log and then do a computation from scratch and come up with a new value of how many cars in the parking lot. Could you do it smarter? What would you do? Instead of keeping the log of every car,
keep just the log of how many cars are in at one time.
Keep just how many cars are in the parking lot at the current time, right? So because that's the only essential part of the history. I don't need to know each and every car that came in, each and every car that went out. I only need to know how many cars are in the parking lot. And then every time a car comes in or leaves, I just add or subtract to that and do it. So this concept that not all history is relevant, that for any given problem, only a certain part of history, a certain function of the history that is important, is the concept of state. So the state is the information that we really need to remember. Okay, that's the essence of the history that I need to keep track of, and anything else is unnecessary. And our goal from a design point of view would be that that is the information that we would like to keep track of. So there are two ways of coming at it. One is you can say state is what a circuit remembers. And the way I kind of just described is state is also the essential history that a circuit needs to remember. Okay, if I don't remember enough of the state, then I cannot do my job. If on the other hand I remember the entire history, then essentially I'll have a log which just keeps growing, 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 and that would be infinite amount of memory. So a infinitely sized state, which is not very good. So the idea then is that we analyze the problem, figure out what is it that I truly need to remember, make sure that there is a way for my circuit to remember that, and then every time something happens, like a new event happens, then I update the state. Okay, so and my output now depends upon what my state is also. Okay, so we'll see how that works out. There are this notion of updating the state, which means that I'm storing some factoid about the history in my memory. Every time I see something new, I update that factoid, and my output, anytime I have to answer something, I not only look at what the input pins are, but I also look at what my memory is. Okay, and if you think about it, that's how we operate also, right? I mean, our brains are not simply whatever is the current thing we are sensing, and then we base upon that. I mean, if you think about it, like right now when I'm talking to you, I'm not just saying what I'm seeing on this slide. I'm obviously making use of my experience or memory or whatnot to kind of add stuff to whatever is on the slide. So you can say that I'm a sequential system which has state, which is kind of a summation of my experiences. Of course, my brain has a finite number of neurons, so while we can remember a lot of things, our brain actually does discard old memories because we just do not have enough space to store each and everything. I mean, no human being, I think, remembers each and every scene that we have observed through our eyes. We just do not have that amount of memory. So our brain continuously builds up memories in more compact form. Circuits do the same thing, have to do the same thing, because otherwise we'll have a blow up of hardware. So updating the state information is very important, and then becomes the issue, more of an engineering issue. How do I update this state? So one possibility is we keep updating the state whenever something interesting happens. I see an event, I update it. I see another event, I update it. The problem that happens is that Mother Nature does it very well in our brain, but as engineers, we soon run into trouble with these kind of approaches. So instead, the easier engineering approach that people have developed is a notion of having something called a clock. So the idea is that we will update the state not continuously, but only at tick of a clock. So like every 1 second, I'll examine the state of the world, state of the input, okay, and update my memory. And then again, when the next clock ticks, I'll do the same thing. If anything happens in between, I'm not going to be aware of it. Okay, and this turns out it simplifies circuit design considerably. So it's kind of like if our brain were to only observe things at certain quantum of time. Okay, and actually that's what our brain does also. Deep down, we actually do have a clock in a part of a brain called hippocampus, but that's an aside. Point is, this having this clock to pace the circuit is a very essential part of engineering these things, and it's called synchronous design. So we are synchronized with a clock, and in between, what happens to the inputs in between doesn't matter. We are going to look at the input and update our state only at a clock tick. The essential memory elements is, at the heart of it is something called a flip-flop. Flip-flop, it's called flip-flop because it basically can store one bit of information and it can change it. Okay, it can go from 1 to 0, 0 to 1 as the need arises. So you can think of memory or state which as nothing but a bunch of flip-flop, and so that constitutes a memory. Each flip-flop at any given point in time could have a state of 1 or 0. So if I have 10 flip-flops, I have 10 bits of memory, and therefore I can store 2 to the power 10 distinct states. Okay, so a system which has 10 flip-flops would be capable of representing 2 to the power 10 different states, and entire history of inputs it has seen have to be classified into one of those 2 to the power 10 states. Okay, um, uh, modern chips and all may have tens of thousands of flip-flops or even more. Okay, so they have much larger amount of states, obviously, than the example of 10 I gave. But that's the heart of this D flip-flop or data flip-flop. And if you go to Logisim, you'll see this as a module available to you. Another concept that we'll see shortly is something called finite state machines. So the idea out here is um, that if you look at computers, um, there are many different kind of computing machines. What's the most powerful computing machine? In an abstract sense, that is something which can do that any other computing machine can do. Now, digital is a way of implementing. So early in the course, I kind of talked about a little bit about Turing and kind of the movie and all, the so-called Turing machine. So the Turing machine is a mathematically abstract or an idealized computing machine, and whose main claim to fame is that anything that can be computed by a Turing machine. So it's the most powerful form of computer that could be there. That is, if any problem is solvable by an algorithm, then a Turing machine can do it. And if a Turing machine cannot do it, then nothing else can. Now, Turing machine is an idealization. In fact, it assumes infinite memory. Okay, so obviously it doesn't work. But then there is a hierarchy of simpler and simpler computing machines, and the one among the very simplest one is something called finite state machine or finite state automata, or a bunch of different names that it kind of goes under. And we are going to talk about that, and we're going to talk about how we can design state machines. Now, it turns out that all computers that we make, okay, because they are intrinsically finite, they are actually no more powerful than a finite state machine. But how we think about them, so in many cases, we think about them as approximations of a Turing machine, and whereas in this course, and that those of you computer scientists will probably see in your automata class and all, but here we are going to just look at these finite state machines. Finite, and as you can see the term finite state, that basically means they will have a finite amount of state, and since state is stored in flip-flops, so they basically translate into a finite number of flip-flops. Okay. So let's see how it kind of works out. So combinational logic is memoryless. So output is a function of input, and if I had infinitely fast gates, this idealization is perfect. If my gates have some physical delay, so you can basically say output is always tracking the input after a little bit of a delay. Okay, but point being that if I change the input, then after a little bit of settling time, the output has a value, and that value depends solely on the value of the input. If I change the input, again after a little bit of time, output will change to a new value, but that new value would be only a function of the new value of the input. It will be independent of what was seen previously. Sequential logics are different. What sequential logic do is that, and that's on the right hand side, that they have a more complicated structure. So they have an input, they have an output, but then they also have something called state. And the idea is that at all times, not only are they computing the output, but they're also computing the next state, the next set of memories, if think of it that way. So we are observing the input, and we are computing output, but we are also building the next set of memories, and we feed that back because I have to store that memory in again out here. Okay, so and conceptually, again taking the brain analogy, that's how we work. Our senses are like our inputs. Always we are looking at our sensory stuff. Our actuators, like our hands and whatever, our vocal cords and all, they are kind of like our output. But then as we get the sensory input, we continually, our brain is also building up the memories, changing our neuronal structure and all. And then anytime we output something, our outputs are not just what we are currently sensing, but it's also making use of our memories that our brain has learned, skills that the brain has learned. Same concept out here, that that the state is being stored, and every time we are updating the state, and then anytime we compute the output is not only a function of the input, but also a function of the current memories, the current state. So then the question boils down to how do we build that up? And again, state is, as I mentioned earlier, relevant information about the past. We don't want to remember everything about the past, because that would mean to keep a record of every input seen, what time they were seen at, and what sequence they were seen at, and all. We don't want to do that, but rather we want to store just the relevant facts about the history that are important for us to compute the output. Okay, so in our parking lot example, our state was the current number of cars in the parking lot. That's all that mattered to us. And probably the hardest part about this type of problems is to figure out what state you need to maintain. Okay, and when you write software, you do the same thing. The state in software corresponds to the variables that you have and whose value you have to remember. Okay, so that's kind of what's happening out here. Okay, so how do we remember the state? So how can we remember the state using circuits, using gates and all that we have seen? So let's look at an example. So let's look at this structure. Okay, so we are using a couple of gates. It's actually two NOR gates. There's a NOR gate here, and this second guy is also a NOR gate. But this is a different type of circuit that we have seen in the past, because I have this feedback. The input of the left NOR gate is actually connected to the output of my gate. Okay, so this has a feedback, and this in turn begins to have kind of an interesting behavior. So let's call the two inputs S and R, and let's call this intermediate guy X, and let's work out the equation for Q. So Q is going to be not R and not X, just simply out here. X in turn is a NOR gate, so it's not of not X is not of S or in the previous value of Q. Okay, and that results in not R and S or Q old. So this is my equation, that anytime Q is equal to not R and S or the previous value of Q. And so let's see. So if let's say R was 1, then Q is 0 unambiguously. If R is 0 and S is 1, then also Q is 1 unambiguously. But if R is 0 and if R is 0 and S is 0, then Q is Q old. Okay, so now the circuit holds its value. Okay, so its truth table is kind of an interesting type of table, and it looks like this. R is 0, S is 0, then Q is 0, and Q old is 0. If R is 0, S is 0, and Q old, namely the current value of Q is 0, then the next value of Q would still be 0. If R is 0, S is 0, and the current value of Q is 1, so Q old is 1, then the next value of Q will be 1. So essentially Q is equal to Q old. If R is 0, S is 1, then output is always 1. And if R is 1, then Q is always 0. So R is acting like a reset. It's outputting 0. S is acting like a set. It's setting the output to 1, but reset gets a priority. And if both of them are 0, the circuit maintains its state. Okay, if R is 0, S is 0, then Q is just the previous Q. So it's now remembering the past. In terms of kind of a pseudo code, you can think of it: if R is 1, then Q is 0, else if S is 1, then Q is 1, else Q is Q old. And this little thing, we are not yet at a D flip-flop, but this little circuit is now beginning to move us towards remembering stuff. Okay, that suddenly the output depends upon the past. So let's take an example. Let's say I give to this circuit R equal to 1, S equal to 0. Then Q will become 0. then let's say I pull down R. So R is 0, Q is 0, so S is 0. The output will maintain the value 0. If on the other hand, so let me draw it out. Okay, so let's consider two possibilities. One, so I'm going to write it as R comma S. Okay, so let's say we start out with 1 comma 0. The output would be 0. And then let's say I move to 0 comma 0. The output is going to be 0. Let's try a different scenario. We fed it 0, 1. What would be the output? 1. Then I go to 0 comma 0. What would be the output? 1. So now you can see the difference that at this point in time, the inputs are 0, 0, but depending upon what the history was, the output is different. Okay, and that's different from the circuits we have seen thus far, right? I mean, in the previous circuits, if the input had certain value, output would always have a corresponding fixed value. But in this particular case, how we reached 0, 0 matters. If we reached it from first having 0, 1, then 0, 0, then the output is 1. If on the other hand, we first saw 1, 0 and then saw 0, 0, then the output is 0. So this is a circuit whose behavior depends on the history. And now we can begin to do interesting things. Okay, that's sort of what we'll build up towards. Okay, so this is probably the simplest possible historyful circuit that you can imagine. So I have tried to let me kind of just jump through. Okay, so there's a timing diagram, and I think now that when we are talking about historyful circuits, time matters. Okay, because over time things are changing. So these kind of diagrams are called timing diagrams. We saw some of them early in the course, but we'll see more and more now. So what I'm doing is I'm drawing what the value is on the signals R, S, and Q. And what you are seeing is like R goes from 0 to 1, 1 to 0 at certain times, and the times are indicated by these times. So like at time t1, R goes from 0 to 1. At time t3, again R goes from 0 to 1, and so forth. These arrows that you are seeing, like from an edge to this other edge, this is a notation used to mean causes. So this is basically saying the R going from 0 to 1 causes Q to go down to 0. Another thing that you would see is if you look at this early part of Q, I have written it as X. And this basically means I don't know what Q is. Okay, it could be 0, could be 1, I don't care. Okay, so now let's see what's happening out here. So we are starting out, R is 0, S is 0, I don't care about Q. Q is the output, it is in some state depending upon what happened previously. So if it is 0, 0, our timing diagram tells us that Q maintains its state. Okay, so as time passes here, R remains 0, S remains 0, so Q remains whatever its unknown state was. Then at time t1, R went from 0 to 1. So when R goes to 1 and S is still 0, then we are in this last line of the truth table, and that says Q should go to 0. And therefore, R going 0 to 1 causes Q to go to 0. So after a short delay, we know for sure that Q has the value 0. Okay. Even if my gates were infinitely fast, Q cannot happen before R, because the R going from 0 to 1 is what is causing Q to go to 0. So there's a causal dependency out there. Then for certain time, R remains stable. And then after a while, R goes back to 0. And then from this point onwards, R is 0, S is 0, and Q maintains its state. Then at time t2, S becomes 1. S goes to 1, R is still 0. And looking at our timing diagram, R equal to 0, S is equal to 1 means Q has to be 1. So we see, again, as a result of this edge, Q goes to high after a teeny bit. And this whole process continues. So, and you can kind of keep following each one of them. So what's happening is that at any given point in time, whenever R is 0, S is 0, the value that Q has depends upon how we reached there. Okay, what happened in the past. So it's remembering the history. And this circuit is called an RS latch, reset set latch. The reason it is called a latch is because it does not have a clock. We have not shown you anything with a clock yet. The term flip-flop is used for things which have a clock in them. Okay, so we'll come to that later. So it's called an RS latch. You can draw it many ways. This is how we were drawing it. You can also draw it this particular way. It's exactly the same circuit. Okay, all I've done is I've replaced this AND gate with bubbles at the input by a NOR gate and then kind of position them like this. So oftentimes in books and places, you might see this. These two are exactly the same circuit. They are both are RS latch. Any question on this thing? Any confusion on where we are getting this memory from? Okay, so let's move on. So even this simple circuit can be useful. So let's look at kind of a very simplified example of a sequential system. I'm sure all of you have traveled on airplanes, and you know there are these buttons on top of your seat, which are the flight attendant call buttons. And the way they kind of work is you press them, they'll light up, and then they remain lit up until the if the flight attendant comes, and when he or she comes, they basically press it again and it goes back to 0. Okay, so what's happening is that there is, in a sense, there is a calling and there is a canceling thing, which is I'm lighting up the light and then I want to cancel that light. So the logic I want to design is kind of like the following: that I have some system at the output of which is our light bulb, and what I want to do is whenever I press call, this should light up, and whenever I press cancel, it should go down. But of course, what is going to happen now is that much depends upon what the history. So for example, if the bulb is already lit up, then pressing call should have no effect. And likewise, if the bulb is already off, then pressing cancel should have no effect. So this is a great example of just using the RS latch. So let's see how it will work out. So starting state, light is off. Then we press the call button, the light goes on. Release the call button, light stays on. Okay, so while I press the thing, this line was 1, and I'm using my good old SR latch. So I write the call button to the S thing. So now I'm in 1 0, and from our truth table, 1 0 means output becomes 1. Then I release the call button, I go back to 0 0. 0 0 means remember the past. So at this stage, the light bulb stays on. Then the flight attendant comes, presses the cancel button. This guy goes high, and as a consequence, R is 1, S is 0. The output is 0. Light bulb goes off. We release the cancel button. The light bulb remains off. So that's all that's happening. Internally, it's just our SR latch. Okay. So okay. So what happens if call and cancel are pressed simultaneously and released together? What do you think will happen? So call and cancel being pressed simultaneously, what are our two inputs? 1, 1. So what will be the output? 0. And I release them, 0, right? So it will remain 0. Now that's the simple RS latch. Now, and you can actually design any sequential circuit using that kind of a latch. Okay, and in fact, one way of thinking about neurons in our brain is a little bit like that. I mean, we do not quite operate that way. Our neurons fire in time and all also, but conceptually they're working. You can think of them as like a gigantic network of these kind of elements. But as I mentioned earlier, because of reasons of engineering, to simplify engineering, the engineering of digital systems usually is done using a clock, so that the change of state happens only at a tick of a clock. So let's see how that works out. So with RS latch, what happens is that the state can change at arbitrary times. Whenever the input changes, then after a bit of a gate delay, the output will change. Okay, and such behaviors are called asynchronous, and the problem is it can lead to immensely complicated engineering. So what is done is that digital systems are designed using a notion of a clock. Clock is nothing but a periodic signal which goes from 0 to 1. Okay, in its simplest form, you can think of it like that. The edge of a clock is when the clock goes from 0 to 1 or 1 to 0, and it does so in a periodic fashion. A few lectures ago, there were a bunch of questions about clocks, which are generated by these oscillators and things like that, but none of that really matters. At our abstract level, clocks are a signal which takes values 0 and 1, and it moves from 0 to 1 and 1 to 0 in a periodic fashion. And frequency of a clock is number of times it changes from 0 to 1 in a given second, or vice versa. Period of a clock is from one edge up, let's say one edge which goes from 0 to 1 to the next edge which is going from 0 to 1. So what now begins to happen with these systems is the following: that I have some, instead of our RS latch, I have something else, and you'll see that it's a flip-flop, and that flip-flop has a clock input also. And what happens now is that unlike an RS latch, where whenever the input changes, the output would change immediately, what this guy does is only when the clock ticks precisely at that edge, it is going to look at its input and updates its memory. Okay, so you can think of it as a storage area, and the entry to the storage area opens for a tiny bit of time when the clock has a tick, like clock goes from 0 to 1. At that time, the input is copied into the storage area, and then after that, we ignore everything. And then the next time the clock tick happens, we just again look at the input right at that time and do it. So it's kind of like, conceptually, it would be kind of like, let's say if we were leading our lives, like every clock tick, I would open my eyes, take a image of the world, assimilate it, close my eyes, then again next clock tick I were to do it. So the in between the clock ticks, if there were any changes in the state of the world, it won't matter to me. So I opened my eyes, the room was like this, closed my eyes, something happened in the room, I will not see it. I opened my eyes, if there was a bird which came in and went out, in between opening my successive openings of the eye, I will never realize that, okay? Because I am soaking in the world around me only when I open the eye, only when I bother to look at the world. So what this guy is doing is, it's looking at the input only when the clock tick comes and never else. So that's a very important concept. It's a bit of a tricky concept to understand, but turns out to be very useful. Question?
So when it ticks up, it looks at its input. When it ticks down, it does nothing.
No. So let's be very precise out here. My clock will look like this. Okay. When I say tick up, I literally mean this edge. Okay, not when it is high. I literally mean at the edge. Okay. Now you might quibble that how can I design circuits which only look at the edge and all, but trust me, they can be done. They very tiny time window, picosecond type kind of thing, but just at that time it takes a snapshot. Okay, so it's like, again, look at your video cameras, right, or movie cameras. They take frames of the world, right? So what happens is your shutter opens, takes an image, closes, then again a bit later shutter opens, takes the next image, closes. So the video that we get is really a succession of images taken at a certain rate. Just as an aside, so when we watch our movies and all, or TV, how often do you think like successive images on the video, how far apart are they? 24 is the movie, the Hollywood type cameras. Our TVs use something called NTSC standard, and that is actually 29 point something, so almost 30 images per second. Okay, so Okay, I'm a little confused. I think it's a 29 something millisecond apart, or 29 times it, roughly 30 millisecond apart, 30 images a second. Okay, so in between, if something happens, the camera cannot capture it. Okay, again, if that bird came in, flew away, all within that gap of 30 milliseconds, tough luck. So I'm viewing the world at these snapshots. So that's how this guy is operating. All it is it has memory. It just copies the input, but it copies the input whenever the clock tick happens, and otherwise the output it is showing is whatever its current location is showing, current memory is showing. So it's just a dumb little device. It's just storing the value and outputting that value, but it updates the value only at the clock tick. Okay, so that's my clock, which I had also drawn in the previous slide. Okay, so that's our storage circuit. All it is doing is it's remembering stuff, and at any given point in time, that's its output. So now let's see how. Now the claim is any memory-oriented circuit I can design with this kind of structure. That is, I have the storage device, and everything else is a combinational logic. But this combinational logic has a very specific structure to it. And that structure is the following. You can think of this combinational logic to have two parts to it. There is one part which we'll call as output logic. And what it does is, at any given point in time, it takes the input as well as it looks at the current state. Okay, so this part you can think of as what the current state is. Remember, this guy is always outputting whatever it has remembered on these wires. Okay, so what my output logic is doing is it's looking at the input, it's looking at the current state, and then it's computing the output. Now, if my input signal changes, then the effect of that can bleed into the output immediately. But my current state can only change at the clock tick, right? Because that's how this guy is designed. It only updates its state at the clock tick, and therefore current state can only change at the clock tick. This output logic is basically what this guy is doing is you can think of it as it's a function of in comma current state. And that's what it is computing. Next state, this is another piece of logic, combinational logic, and it's doing the same thing, except that its output we feed back. So this is also combinational logic. It's computing a different function, g of in comma current state, and let's call this thing next state. So what we are doing is that again, combinational logic, two independent parts to it. One of them is computing the output, which I'm sending to the outside world, and the other I'm computing what the next state is. Now let's see what's going to happen. A clock tick comes, a new value got put into the state. That value will appear on current state after a teeny bit of time. This next state logic is going to take that, and let's for now imagine that input is stable, or okay, and then what will happen is this next state is going to compute and come up. Next state logic is going to compute a signal called next state, and at the next clock tick, this guy will read that in, and so forth, right? So now, meanwhile, this input, let's imagine it is coming from a similar circuit. So this input itself is coming from a previous sequential circuit running on the same clock. So this input is also going to change at every clock tick. So at every clock tick, the previous stage is going to change input. A little bit after the clock tick, input would have changed. And meanwhile, we ourselves are changing the state, current state value, a little bit of the clock tick. And so what we'll see is, if you were observing the circuit, after every clock tick, out will change and next state will change. And then the next clock tick will come a bit later, and same thing will happen all over again. So we are kind of pacing the circuit that way. Questions? This is very important to understand. Yeah.
So if you're triggering everything off the same clock, and there's some inherent delay in the system, wouldn't that possibly mean that if your clock is faster than what your internal delay is, then you're going to have like race conditions?
Excellent question, and that would be the topic at the very end of the class. Okay, it's So right on. So the point that he's bringing out is the following: that if remember I was saying these things changes, they all have delays, right? Combination logic has delays. If the combination logic is sluggish and my clock is too rapid, then next state may not be ready before the next clock tick comes in, and then I would have problem. So the answer to that really is that I need to make sure that my clock ticks are coming slowly enough, and that may happen. Let's say, for example, the next state logic happens to have that adder that I talked about previously with this long delay, or it may have a multiplier in it, or it may just take a lot of time. So if next state takes, let's say, 100 nanosecond to do its job, and my clock tick is coming every 10 nanosecond, I have trouble. Okay, so sort of flippant answer to your question for now, sufficient answer to your question now, is that I have to make sure my clock ticks are slow enough. Okay, but there are a lot of other issues that sort of come up which we are going to see. Any other question on this? Okay, so these kind of circuits where I have this next state and output combinational logic and all are basically implementing finite state machines. Okay, so they are also referred to as finite state machines. And the idea out here is the following: it depends upon, remember I said the state is like memory, which is reading its input at a clock tick. So a question then becomes how many bits this memory is storing, right? I mean, how many bits can it remember? So if it can remember n bits or s bits, then the number of distinct pieces of information it can remember would be 2 to the power s, because each bit has 2 states, and if I have s bits, then 2 to the power s distinct patterns can be stored. So my entire history has to be classified into one of those 2 to the power s possibilities. Okay, so for example, in going back to my parking lot example, since I wanted to remember the number of cars in the parking lot, then the state would need to have how many bits?
However many to store that number.
Right. So if the car parking lot, let's say, had 400 spots, I would need 9 bits. Okay, because I need to store all numbers. Parking lot could be empty, could have 1 car, 2 car, all the way up to 400 cars, right? So there are 401 possibilities. So I need 9 bits for that. So you need to. So the idea is that you have to analyze the problem and then see how many distinct cases of history you need to remember, and that's the minimum number of bits you need. Now, oftentimes we use more bits so that our logic becomes simpler, but that's at least the minimum number of bits that I need to remember. A couple of there's one other thing that comes up, that these, depending upon what the structure of this combinational logic is, there are two important cases that arise, and they all have been given names. One is called Moore machine, other is called Mealy machine, or Mealy FSM and Moore FSM. So let's look at so superficially the left diagram and the right diagram look exactly the same, but they are not. So one thing you would see is that in case of this Mealy machine is like what I had in the previous slide. Output depends upon input and current state, and next state depends on input and the current state. But on the right hand side, if you look at, the output depends only on the current state. Output does not depend upon the input. Input only affects the next state logic. Okay, so that's what I've written. Output is a function of state and input in MIDI, but in case of Moore, output is a function of the state only. Why do you think we might do that? What's the advantage of the right structure?
Easy to design.
Okay, why?
Because thus on each state we only need to consider, like the output, we only need to consider state instead of the input.
Okay, so my combinational logic is simpler. Oh, output, okay, fair enough. But do you see some? Can you think of some other advantage?
You get to put a delay in your circuit.
Which actually is a bad thing, right? I mean, because if my input changes, here the output can change immediately. There I have to wait until the next clock tick, right? Okay, but nevertheless, I think I had only asked what's the difference, so fair point. Okay, so so that's a disadvantage. Okay, can you see some advantage on the right hand side besides the one he mentioned?
Like they both get the value at the same time, like output and next state.
Output and the next state. Well, I think you're kind of headed to it. So the main point is output will change now only at clock ticks. So if input were to change in between clock ticks, it's not going to have an impact on us. Now, why might that happen? Previously, I said input may be coming from a similar piece of logic. But that's not always the case. Our computers have to interact with the outside world. So, for example, when you press a key on the keyboard, we don't press the key when the computer's clock is ticking at its edge, right? We press it whenever we feel like. So when we press the key, it may happen in between clock ticks. And that can, in a circuit like this, that would mean that output will change in between clock ticks. Okay, so whereas something like this, advantage is if you were to put this thing right after the keyboard, then from that point on, I will have an output signal which is at the clock boundaries, at the clock tick only. So Mealy has some advantages, namely simpler circuit, as he pointed out, and this thing that the outputs are synchronized to the changes in the clock. But it has a disadvantage, which he pointed out, and which is that the effect of input has to wait. Output before changing the output. Output has to, if the input changes, output can only change at the next clock tick, not earlier. Okay, so there is delayed gratification. Okay, as a result. Those are kind of the changes. So let's summarize them out here. So Mealy, the advantage is out changes immediately. More, out changes at next clock tick. When I draw something like this, it means an rising edge of the clock or an edge of the clock. It has simpler logic. Okay, so this is how one can think about these two things. So those were our trade-offs. Okay, so now until now I've still magically assumed that this thing can be somehow implemented. I still haven't told you how we can implement it. Okay, so all we know thus far about it is at the clock tick, it reads in the value, and then it stores certain number of bits. Now the module which does so, as I referred to earlier, is something called a D flip-flop. So the D flip-flop is a version of that state logic which is capable of storing 1 bit of information. So the way it works is, it's a module which has 3 inputs, D, Q, and a clock. Anytime you see this triangle, which we also had previously, that means it's a clock input. Okay, so I have D, Q, and a clock. Output Q normally is steady state. Whenever there is an edge on the clock, that is whenever this clock ticks, then at that point in time, whatever is the value on the D inputs is stored in the flip-flop, stored in this circuit. And Q always follows whatever is stored in the circuit. So the Q is always following the memory, and the memory is being updated at every clock tick based upon whatever is on D. So this is storing 1 bit of state. And sometimes you would see, and in Logisim you would see, there might be some additional signals. Like for example, there might be an enable signal. If the enable signal is low, clocks have no effect. It's almost like I stop listening to the clock while the enable is low. Asynchronous set and reset, So I can initialize the memory of the flip-flop. So sometimes they may have set and reset, which basically say if there is a set signal, the moment set signal goes high, the internal memory of the flip-flop is set to 1 immediately. Likewise, if there is an asynchronous reset, if whenever it goes high, the internal memory of the flip-flop is set to 0. You could also have synchronous set and reset. A synchronous set means if the set signal is high, then and the clock tick comes, then the internal state is made to be 1, and likewise for the reset. So you will see if you again sort of browse through Logisim, you would see that the D flip-flop there has all these other options as well. We can take these D flip-flops, tie their clocks together, and make a multi-bit version of this D. So if I need to store S bits of state, then I can take S of these D flip-flops, tie their clocks together because they have to run together, and now I have S bits on the D and S bits on the Q. So suddenly I have a structure like this as shown out here. It's a D flip-flop which has S inputs on the S bit of input and S bit of output, and it has a clock in it. So this is our basic memory structure, which we use in finite state machine. On the clock tick, store S bits of information. And then kind of the trick boils down to is how can we design how can we make use of and design systems which require us to have memory in it. So this is just from our Logisim, where if you go under there is a memory library on the left tab of Logisim. You go under that, you will see D flip-flop. There are other types of flip-flops also. There is JK flip-flop and T flip-flop, and there are other entities like registers and counters and stuff like that. They're all kind of related. Okay, the fundamental one is D flip-flop. Okay, everything else can be made using that. So very important, and this is how the symbol looks like on the right hand side. And then you would notice that under the, I think it's under wiring probably, there is something called a clock. So what Logisim does is it gives you a clock generator. And then within the clock generator, you can even set its frequency. Okay, and I think it can go as fast as some 32 or 64 kilohertz. Okay, because it's simulating the whole thing on your computer. So you can essentially put a clock generator and kind of just sequence through things. So now let's see how these things kind of tend to operate. So let's imagine I assemble a circuit as shown out here. I have some combinational logic. This combinational logic has an input coming in from the outside world. It's producing an output, m bits of output for the outside world. It's computing a next state logic, and then I have this D flip-flop, multi-bit D flip-flop, whose output I take and feed back to the other input of the combinational logic, and this is the state. Okay, and then at initial time, let's say input is A, current value of the state is SA. So what this combinational logic is going to do is it's going to compute the next state, which is a function of A and SA, and let's call that SB. So what's happening is, if you look at initially what is happening is that in SA, state, which is the output of D flip-flop, is SA, and the next state logic, this combination logic, the next state it is computing is SB, which is some function of A and SA. So now so this is how we are starting out. Now a clock tick comes. So at the clock tick, what will happen is this flip-flop is going to read its input. This input is SB. And as a result of that, after a tiny bit of delay, the output of this flip-flop will become SB. So if I look at the clocks out here, see this clock tick came, and after a tiny bit of time, the state became SB out here. Because at the clock edge, the flip-flop read its input, which was SB, and dumped it onto the output. Okay, so now I have the state will become SB. So after a short while, so in fact, SA will move to SB. And then this process will repeat. So what will next happen is, so this becomes SB after a short while. Then a new input comes, B. So see out here, after a short time, B arrived. Now the whole process will repeat itself. So what will happen at this stage is, because this is B and because this is SB, there will be a new value SC out here, which is a function of B and SB. And so that's what we see out here on next wire. I'm going to see SC. And then the clock tick will come again. At the next clock tick, I would see that the output state, the output of the flip-flop will change to SC because this guy was SC. So what we'll see is that, this guy changed to SC. And this process will repeat again and again. Input will again change. I think I'll probably run out of animations. Okay, input again changes to C, and I have the next state. I have the state out here as SC. So after a short while, I will see an SD out here. Again, at the next clock tick, the same process will repeat, and this will kind of keep going on. So every clock tick, the flip-flop reads the new value of the state. This new value of the state depends upon the current state and the current input, and then the state is updated and kind of the whole process repeats itself. Okay, and we have to just keep sort of making sure that as there was a question raised earlier, that these are physical systems, so we have to make sure that the desired value of state is ready prior to my clock. That means my combinational logic is fast enough. Okay, if the delay through combinational logic is slower than the time period of my clock, then bad things will happen. So my clock period has to be larger than the delays through my clock. And in fact, the actual constraints are a little bit trickier, but for now that will suffice. So this process keeps going on. I'm not going to repeat, but don't know how long it goes. Okay. Yeah. So that process kind of keeps going on. So let's look at an example. Let's say I want to create a counter. So in the homework, I ask you to make an incrementer. So unfortunately, this is a part of it is a solution to that. So, but in any case, I want to create a counter. So what I mean by that is that I have a state register, which let's say I have initialized. Okay, and then what I want to do is every clock tick, I want to increment the content of this register. Okay, so in this case, you can think that my output is actually nothing but I'm monitoring this guy. This is also my output. So I'm observing this memory, and what I'm doing is I'm incrementing at every clock tick the content of this memory. So one way of thinking about it is this is a system which outputs how many clock ticks it has seen modulo 2 to the power n, because I only have a finite number of bits. I have n bits out here. So what I'll do is this is the count. This is also my current state. I take this current state and add 1 to it. So I take an adder and add 1 to it. Okay, you can do this thing smartly. I mean, an adder is kind of a dumb way of doing this, but it's fine for our purposes. So this input to the D flip-flop, which is our next state, is nothing but current state plus 1. So at every clock tick, the state becomes the previous state plus 1. Okay, and then at some point, since I have only n bits, so this thing will reach 2 to the power n minus 1, that is all ones, and after that it will roll over to 0. So it will go from 0, 0, 0, 0, 0 to all 1, to 1, to 2, to 3, all the way to all ones, and then wraps around to 0. Okay, so that's what this guy will look like. So if n was 4, or whatever, if n was 3 as shown out here, so it will go like, let's say we started out with 0, 1, 0, so it will go to 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 0. So this is where rollover is happening, and then 0, 0, 1, 0, 1, 0, again back to the same thing. So this is a very simple counter. It has many uses. Okay, let's talk about some. Okay, so let's look at, so at every clock tick, I am moving from one count to the next count. Let's say I was observing the least significant bit. right? Let's say I was observing the least significant bit of my count. What do you think would that signal look like? So let's imagine my clock was a 100 megahertz clock. Okay, so every 10 nanosecond, the clock was going high, and then goes down after a bit, and then again goes high 10 nanosecond later, and so on and so forth. So my clock is a 100 megahertz signal. What do you, if I were to observe just the least significant bit of count, what kind of signal would that be? Nope.
They switch every one clock cycle.
So
Like everyone, it was one, and then after one clock cycle, like another going up, like the edge going up, you're going to flip to the 0.
okay.
And then we just keep continuing forever.
So can you describe to me in plain English what that signal would correspond to? So again, my clock was 100 megahertz clock.
Oh, 50.
50 megahertz. Okay, so the point he's making is at every clock tick, my lowest bit is going from 0 to 1, next clock tick 1 to 0, 0 to 1, 1 to 0. Okay, so it's essentially what's happening is if I only focus on 0 to 1 transitions of this thing, it happens every alternate clock tick. It happens out here, next time it will happen out here. Okay, so every alternate clock tick, this signal is rising, and therefore its frequency is going to be 1/2. So if I started out with a 100 megahertz signal, the least significant bit will look like a 50 megahertz signal. What about the middle bit? Anyone else? From back of the room? Middle signal? What kind of signal would that look like? Middle bit of count? 25. Same thing. You would see that now what's happening out here is doing every 4th clock cycle. And the next one is going to be 1/8, so that would be 12.5 megahertz, and so on and so forth. So actually my counter is also acting as a clock divider, right? I start with a clock and I want to generate slower clocks, power slower by some power of 2, I can make use of that. So there are sort of besides doing kind of this keeping count of stuff, there are other things I can do. Let's say I don't want to count up on every clock tick. I only want to count up on those clock ticks where my entry sensor on the parking lot was saying there was a car at the entry. Okay, so every time there's a car entering, the sensor puts out a high, and only then I want to increment. So this is maintaining a state of how many cars are in the parking lot. So obviously I don't want to tick on everything clock. I want to tick only on those clocks where the car is entering, and for the moment imagine a car can enter faster than a clock period. Okay, so how would you design that? How would you design this, change this design so that I count up only when a clock tick is happening while some signal is high?
You like feed the input into the clock so that only once the signal goes through when my input.
No, so how would you do that? Well, clock is feeding out here, so you want to change something to the clock? Yeah. So let's imagine that I have a signal called enable, which I want to feed into this circuit, and the behavior is only if enable is high should the counting happen. Otherwise, count should hold its value.
Why do you pick the one depending on whether I want? You could have the one like okay, it's 0 if there's no car that goes by, right?
Yeah.
And then if the car goes by, you like.
Yeah. So you're right. I just tie this thing to this. I just where I currently have 1, I just make it enable. Right? That does the trick. Can you suggest some other solution?
You just hand the clock like your
That's the other solution. The other solution is that I can put an AND gate out here and put an enable to it. That can also do the trick. The first is a good design. The second is a design to be generally frowned upon, at least for neophyte designers. You could use it, but very, very carefully. In this course, thou shalt not use it. Okay, so main thing is this is called clock gating. And that's a bad thing to do. Okay, don't do it. Again, expert designers do it, but you really got to know what it's doing. In most digital textbooks, usually it is listed under one of the no-nos in digital design. Okay, so but again, there are very valid reasons one needs to do it at times, but honestly, very careful. But in any case, at least purely from a logic perspective, both approaches can work. I can stop the clock, or I can do this enable thing. Okay. The reason, by the way, this thing is a bad idea is, let's imagine what happens is that there is a glitch on this signal, some spike on this signal, then that can lead to an artificial clock being there. So one has to be very careful if you're doing this clock gating. Okay, so that's a very simple example. Let's see. I think I'm going to skip this. Okay. So let's see how we can analyze a sequential circuit a little bit more. So what we have is this circuit out here. And so again, combinational logic, input coming in, output going out, next state, I have my D flip-flops feeding back in. So for combinational logics, we had truth table. Question then becomes, how do I think of a sequential logic? And if you think about it, a sequential logic really, I mean, we have this memory part, but the behavior of this guy is entirely defined by what this combinational logic is doing. This combinational logic tells me that given a current state and input, what the output is, and it also tells me given the current state and input, what the next state is. And everything else kind of follows from that. So I can write the behavior of this combination of the sequential logic by kind of this extended truth table, which is describing this combinational logic. And what it is doing is it's looking at input, it's looking at the current state, and it's telling me what the output is and what the next state is. So for example, let's say for this circuit, the behavior was like the following. So input is 1 bit, so input could be 0 or 1. State is 2 bit, so I have two D flip-flops, 2 bits of D flip-flop. So state could be 0, 0, 0, 1, 1, 0, 1, 1. And so I have 8 combinations of input and state. And then I also need to tell you what the output is. Output is 1 bit. And what's the next state? I have given that. So now what this is showing is, if the input is 0 and the current state is 0, 0, then it's saying output is 0 and the next state is also 0, 0. The next line says, if input is 0 and the state is 0, 1, then also the output is 0 and next state is 0, 0. If input is 0 and the state is 1, 0, then the output is 0 and next state is 1, 1, and so on and so forth. So we are given a table like this. This is kind of arbitrarily chosen. Okay, so now what we can do is, with this, there is sufficient information that I can see how, given an initial state, how the circuit will evolve. Okay, so let's say my initial state was that the current state was 0, 0 and input was 0. And the output in this particular case, as the thing shows, is going to be 0. So let's say this was my initial state. I always have to be given that because these are historyful circuits. So where we start is going to affect our future behavior. So now we are in this situation. So state is 0, 0, input is 0. Now what will happen is clock tick comes. So I have to now look at what the next state would be. Well, it says that if I'm at 0, 0 and input is 0, so I consult out here, input is 0, this is 0, 0, so next state is 0, 0. So therefore next state remains 0, 0. Moreover, if next state is, by the time I hit this clock cycle, this clock, the second clock, then the state is 0, 0, input is 1. So output, looking at it out here, state is 0, 0, input is 1. It shows output is 0. So we see an output of 0 out here. Now what happens? So next clock tick comes, it would see that state is 0, 0 and input is 1. We consult out here, state is 0, 0 and input is 1. So I'm going to look at this line, and this says next state is 0, 1. So that's why you see the next state becomes 0, 1. And then out here, the state is 0, 1, input is 1. So that means 1, 0, 1. So output is 0. So we still see the output of 0. Next clock tick, it would see state is 0, 1, input is 1. So it's 1, 0, 1. Next state is 1, 1. And therefore, we see the next state transition to 1. So what's happening is, this is kind of a time direction, okay? Time is progressing. Okay, and so basically, I'm hopping from each one of this. These are the transitions taking place. And that's being affected by this table. So this table is a sufficient description, a complete description of what this sequential system is doing. This table is telling me for any input and state what the output is and what the next state will be. And we kind of consult this and do it. And this therefore also captures the entire combinational logic behavior out here, okay, because the first 3 columns correspond to the output logic, and the first 2 columns plus the last column correspond to the next state logic. So, and I can implement them using all the stuff we have learned thus far, Karnaugh map, combinational modules, and stuff like that. I can apply all of them to kind of design those things. Okay, so essentially we can decompose sequential systems into kind of a bunch of state bits and then a combinational logic. And combinational logic is essentially the complete description. If I were to ask you, describe to me a sequential system, all you need to do is to give this truth table. This truth table has all the information. It tells me how many state bits I have, because I have 2 state bits, and you can see 2 out here also, so the second and the fourth column. It tells me how states transition, that is, how do I move from one state to the next state. It tells me what the output is in any given state, and so on and so forth. So everything is kind of listed out here. So I can analyze or describe a sequential system in these terms. Now the problem is, this is pretty complicated looking. Okay, I mean, particularly I may have pretty complicated looking behaviors and all, and it's not really giving me a sense of how am I moving from state to state. Okay, what is the function that describes what's going on? So from a very different, there's a very different way one can kind of approach this thing. So remember, I had talked about that states tell me how many distinct histories I have to bother about, how many distinct, like I'm collapsing all the history into a bunch of bits, and therefore if I have s bits, that means I have, at any given point in time, there are 2 to the power s distinct situations I can be in. They are describing to me the relevant history. So in this case, there are 2 bits that basically mean that at any given point in time, I can be in at most 4 distinct possibilities, right? There are 4 distinct histories that I have to worry about. And that's what we call a state, the total state. Okay, so if the state were to be a concept, okay, so we can say there are 4 different values that concept is taking. In our parking lot example, if the parking lot can hold up to 400 cars, then there are 401 different states I have to worry about. Parking lot is empty, parking lot has 1 car, parking lot has 2 cars, so on and so forth, until parking lot has 400 cars. And that's all I need to keep track of. And then find a way. So what is done to deal with this is a very different formalism gets used, and this is in terms of a graph. Now, I'm pretty sure you have seen graphs in one shape or form in perhaps in your programming classes, perhaps in your math class and all, but kind of the intuitive idea is that a graph consists of nodes and edges, and they're used in many disciplines. These nodes have some meaning attached to them, and the edges have some meaning attached to them. We are going to use them in a very specific way, which is called a finite state machine graph, or a state diagram, or a state graph. There are many different names for it. So it's a graphical description of a sequential circuits functionality. So remember, I said I could be in 4 different histories, right? 4 different possibilities. Each one of those state each one of those possible histories, I'm going to capture as 4 distinct nodes. 0, and for here I have just labeled them as state 0, 0, state 0, 1, state 1, 1, state 1, 0. So I give them names. And then, depending upon my input, whenever a clock tick comes, I'm going to move from one state to another. And furthermore, I may have some output associated with it. So let's say I was in the state 0, 0. My current state was 0, 0. And let's say the input was 0. So I'm state 0, 0, input is 0. Clock tick comes. What is the next state I will go to? I'll go to state 0, 0. So I show that by this self arrow. So I'm basically saying if I'm in state 0, 0 and the input is 0, so this you see out here on the edges, I have this thing. So this corresponds to input, comma, input slash output. So it's basically saying if I'm in state 0, 0 and input has the value 0, then my next state is that I stay put. Okay. If on the other hand, if current state is 0, 0, I'm here, and input is 1, then the next state is 0, 1. So I see this arrow going out here, which basically saying if input is 1, the next state is going to be 0, 1. Furthermore, I also need to talk about what the outputs are going to be. So in this particular case, I'm saying if input is 0, and I'm in state 0, 0, output is 0. And if I'm in state 0, 0 and input is 1, output is still 0. Okay, so you see out here, I'm in 0, 0, 0, output is 0, and 1, 0, 0, output is 0. So the second stuff is saying what the output is. So, and the basic idea continues. Let's look at if I was in state 1, 1. If I'm in state 1, 1 and input is 0, so I consult out here. If input is 0, I'm in state 1, 1. Next state should be 0, 1. So you see from 1, 1, I have an arrow going to 0, 1 when the input is 0. And from 1, 1, if input is 1, next state is 1, 0. So I see 1, 0. So if input is 1 and I was in 1, 1, the next state is 1, 0. So each one of these edges can be derived from this table. Or vice versa, I can derive this table from such a graph. This graph is telling me how I am moving from one state to another state, and also what is the output that I am kind of doing. So let's going back to our parking lot example. Let's say I want to have a display outside the parking lot, which basically activates a parking lot full sign, right? So remember I talked about that I will need a whole bunch of states. I'll need a state for parking lot being empty, a state for parking lot having 1 car, 2 car, 3 cars, all the way to 400 cars. Okay, and then when I'm in the state for 400 cars, then at that time the output that parking lot full sign should light up, and then otherwise every time a car enters, I move to the next higher state. Every time the car exits, I move to the left state, one less state. Okay, so that's how one could kind of structure that. So the key thing out here is, given a problem, you'll have to kind of analyze what the behavior is. So let's go back to our counter, which we had out here. Okay, what do you think its state diagram looks like? So let's say I have a 4-bit counter. So let's say I have a 4-bit counter. What do you think its state is going to? 4-bit counter with an enable signal. So firstly, how many states would I have? 16, right? Because 4 bits to the power 4, 16. Let's call them count 0, count 1, count 2, all the way to 15. Okay, and I have an enable signal also. Okay, so I'm in state 0. enable is low, what will happen? So self, and if enable is high, I move to the next one. So okay, what am I outputting out here? So if I am in state 0, I'm outputting the hex number 0. Okay, so I can write it as hex 0. And likewise in state 1, I'm outputting state 0. Here also I'm outputting hex 0. Same thing out here. If enable is 0, I stay put, but I'm outputting 1. And if enable is high, I move to the next state, and I'm still outputting 1. And like that. The thing will change out here. We'll have 0 F. In case of 1, I move back to the state 0. So this is my 4-bit counter. That's going to look like. Now it turns out that for more complicated problems, it's easier to start with the state, this kind of a state diagram, because given a problem specification, you kind of think about what are the states, how am I going to move between them, and then translate this into our table, which then we can implement. So the typical design pathway goes that you design the state diagram first, from that you derive this table, and then use the combinational logic techniques to implement that. So to recap this part then, these bubbles, these nodes correspond to the states. These edges are called state transitions, and they're annotated with input/output. And input/output. There's a special case out here that if it was a Moore machine, in case of a Moore machine, so just to test, what's the difference between Moore machine and Mealy machine? In Mealy machine, output changes immediately because it is a function of the input. In case of Moore machine, the output is a function of only the state, right? So if output is only a function of the state, I don't need to put it on the edges. I can actually make it part of the state, right? So in a Moore machine, what you would see is that every outgoing edge has the same output. Every outgoing edge of a node has the same output. That's an indicator that it's a Moore machine, because transitions depend upon the input, but the stuff after the slash does not. So if you look at this one, if I look at state 0, 0, it has 2 transitions. Output is the same, 0 and 0. Let's look at the next one. The output is 0 and 0 on both the edges. Let's look at the next third one. Output is 0 and output is 0. Let's look at the fourth one. Output is 0 and output is 1. So unfortunately, so while these first 3 states were behaving like Moore, the final state is not behaving like Moore. Okay, the final state, one outgoing edge has a output of 0 and the other outgoing edge has an output of 1. And even if there is one such case in my whole state diagram, then it's no more a Moore. This whole thing is Mealy. Okay, even though first 3 states passed our test. But if machine was indeed, if it was indeed a Moore machine, then I can draw it in a more compact way. What about our this diagram? Well, is this Mealy or Moore? This is Moore, because on every state you can see that both the outgoing edges have the same output. And that was sort of also clear from the diagram of the counter. The value output of the counter was nothing but the output of my state register itself. Okay, so that was a giveaway too. So let's see an example. Let's say I want to design a traffic light controller, and this traffic light controller is going to make certain simplifying assumptions, but so that it's not quite real, but nevertheless is representative of kind of light things that you might encounter. In fact, traffic light controller stuff is a great example of kind of a finite state machine at work. So what we have out here is cross roads, so two roads crossing each other. They have traffic lights, and what we also have is car sensor, detection sensors. So this is the kind of stuff that you may see on roadways, those loops that they have where your car comes over and then the system knows that there's a car waiting and then it activates the light. Okay, so it's kind of like that. So what we have is the east-west road, which is the horizontal one, the north-south road, which is the vertical one, and we want to design a state machine. And what we have is on the east-west road, which is a secondary road, we have these detectors, which is telling that there is a car waiting in the east-west direction. And I have an OR gate, which combines the output of these two sensors and gives me a signal called car east-west. So this car east-west signals basically tells me that there is a car waiting either on the east-west road, waiting at the intersection. On the north-south direction, we don't have any such sensor because, as we'll see soon, it is our primary road, so we give it the priority. And what we want to do is, and I have a clock and I have a reset signal to kind of set the whole system into a particular state, and then I want to control the lights. And I have two sets of lights, one for the north-south direction. So essentially, the two north-south lights, so the one out here and one out here, they're controlled the same way, and the two east-west lights, they're controlled the same way. So I really have 6 independent lights: the red, yellow, green for east-west, and red, yellow, green for north-south. Okay, so that's the setting, and then I have to design a system which obeys some rules. Okay, and by the way, kind of problems that you will encounter typically fall into this thing. There's some setting given to you, input, outputs, and stuff like that, and then there's a behavior given to you, and this is the behavior that we are seeing. So the behavior is the following: upon startup, reset to green in north-south direction. So north-south is a primary road, so we are going to give it a green. If light is green or yellow in one direction, it must be red on the other. Needless to say, should be like that. A light must be yellow between changing from green to red. So if I'm changing from green to red, it should go through a transition for yellow. Again, that's how lights behave at traffic corners, or at least should behave. If there is a car waiting on east-west, then east-west should become green before returning to green on north-south. So kind of the idea is that if there's a car waiting on east-west, we are going to turn green for a clock cycle, let that car go, and then go back to green on the north-south. Okay, and if there are multiple cars waiting, this process will keep repeating. And for now, let's imagine that we are designing this system so that our clock speed is slow enough, because we are going to advance from clock cycle to clock cycle. So obviously, we cannot be running at 10 megahertz, 100 megahertz type clocks. Then cars will have to speed a lot. So our signals are running at, let's say, I don't know, fraction of a hertz kind of signal. Okay, so all those simplifying assumptions. Okay, so how should we approach something like this? Kind of idea is you understand what your signals are doing, you analyze these rules. If they are unclear, you talk to the customer or professor or whatever, and then try to come up with the state machine. So as I advocated, the best thing to do is, instead of coming up with that table, that would be totally non-intuitive, you approach this thing in terms of this diagram. Okay, so that's kind of the best way to do it. So let's see how we might approach. So again, finite state machine is specified. So given the input output, I have to figure out the state. Well, what state is relevant out here? Okay, so obviously, remember, kind of the idea was the state encapsulates the necessary information about the history. So I certainly don't care what all cars pass through this intersection since whenever the road was built. Okay, that's irrelevant. There's only kind of all of that history gets mapped into a certain distinct piece of information that we need to know. And what that really translates into is that what is the state of the lights? So what are the possibilities? Well, one possibility is that north-south is green, and by our rules, east-west therefore must be red. Another possibility is north-south is yellow, and again by our rules, east-west must be red. Or east-west is green, and therefore by our rules, north-south must be red. Or east-west is yellow, and by our rules again, north-south must be red. These are, so I would submit that these are the only 4 distinct possibilities that exist in the system. Anyone doesn't agree with that? Right. So if our system is operating correctly, these are the only 4 possibilities that are there. What are our inputs? Well, our input is there is an input called car east-west, which is basically saying, is there a car on the east-west road? I also have an input called reset, which basically says if whenever the reset is there, without going through yellow and all, go back to the initial state, and our initial state is this very first one, not green on the north-south, red on the east-west. What are our outputs? Well, our output, I have to control 6 lights. So I have 2 3-bit signals. So it's basically I'm controlling the lights in a one hot way. So I have 6 signals controlling green, yellow, red for east-west and green, yellow, red for north-south. So, or vice versa. The first triplet is for north-south, the second for east-west. So you can think of I have a 6-bit output, and 1 0 0 0 0 1 would mean north-south is green and east-west is red. Okay, and so forth. So that's the setting, and we have now decided there are 4 states. So next thing is okay. So next thing is we create our 4 states. So remember we said the 4 states are green north-south, yellow north-south, green east-west, yellow east-west. Moreover, in the setting in this machine, you can see that it's obviously a Moore machine because our states correspond to the setting of the light, and the light is the only thing we are controlling. So green north-south corresponds to output being 1 0 0 0 0 1. Yellow north-south corresponds to 0 1 0, so the middle one for north-south, and 0 0 1, it has to be red on east-west, and so forth. So that's the next thing we write. And now finally we write the transitions. So for reset, it means that if reset is high on any one of these latter 3 states, we move to green north-south. Now let's say we are in green north-south. So if we are in green north-south, then if car east-west is indicating there is a car and the reset signal is false, then I move to yellow north-south because I have to turn the light green. Okay, so that's what we are doing. But if on the other hand there's no car on the east-west, or I am asserting a reset, I stay put. If I'm in yellow north-south, then if it is not reset, then I am moving on to turning the east-west light green. So that's what I'm doing. And then after 1 clock cycle of green on east-west, if the reset is false, I move to yellow east-west. And then finally, after I'm done with yellow east-west, I go irrespective, whether it's reset or not, I always go back to green north-south. So what's happening is every time a car comes on, there's a car on east-west, I'm going to turn the light green, I'm going to move to yellow, move to green on the east-west, move to yellow, come back. And if there is a lot of traffic on east-west, this will keep happening. So what will happen then is we're going to just simply alternate between the two. Okay, so we are going to keep green on for 1 clock cycle on north-south, yellow 1 cycle, 1 cycle, 1 cycle, and we'll keep iterating if there's a lot of traffic. If the traffic on east-west side is very thin, then only when the car comes, we kind of give it an access. So that's what the diagram looks like. I'm running out of time, so we are going to pick this thing up after the midterm. So again, Monday midterm, and on Friday evening we are going to do the midterm review session.